This is AP Stats. This is our second topic in unit number 1, categorical variables. So we're going into categorical variables a little bit more in a little bit more detail. So we started off by talking about different types of categorical variables. Today, we constructed a couple of single variable graphs. One of them was a pie chart. The other one was a bar graph, specifically a Pareto diagram. We don't really need to know what the names of these things are. Just a pie chart, how to get that done. Bar graph, how to get that done. Very, very important. Then we're looking at two-way data. Population or samples, anything, observations that are classified with respect to two different categorical variables at once. So in this case, the problem that we were stuck on, that we didn't get to finish today, because technically I could call it like the bell ringing. There wasn't like an actual physical bell that rang or anything like that. But if this were a normal class situation, the bell rang on me. So we ran out of time. This is data that's collected on information on food orders. So these are food orders classified with respect to two different variables. So one of those variables is the style of food, like the ethnic origin of the food, I guess you could say, though fast food is not an ethnic origin unless, well, that's an American thing, most likely. But either way, so the type of food or the style of food, and then what the food consists of regarding the meat or the lack thereof. So beef, chicken versus vegetarian. So we're taking observations and making double classifications here. We're classifying them with respect to two different dimensions, basically. So the first dimension would be the type of protein. The other dimension would be the type of food style, the cooking style. So what we looked at earlier, what we did have time for, was a marginal distribution for just food style. So then what we did here was looked at the column totals because it goes column wise. A different column is a different food style. And we looked at those column totals. In other words, the totals along this margin, and that gave us a marginal distribution. So marginal distribution is where we say, you know what, I don't care about both variables. I just want to know how one variable looks like. So a marginal distribution is where we want to look at one particular variable. We were about to begin with a conditional distribution. So we have these two definitions up on top, which I didn't really take time reading in the class period. A marginal distribution is along the margins, either the row totals or the column totals, which is how one of the variables is distributed without caring about the other variable. So it's a distribution of one of the variables in the contingency table along all individuals, among all individuals described by the table. So here we're not even caring about the other variable, just the one variable in question. A conditional distribution mixes the two a little bit. So what it's going to do is it's going to ask the question, what does this variable look like for just a specific value of the other variable? So let's say I'm interested in knowing, well, what's the breakdown on Chinese food? All right, so let's just talk about Chinese food specifically. What's the breakdown by protein type? Beef, chicken, and veggie. That's exactly what this problem is going to ask for. Give a relative frequency bar graph, and that's the type of graph showing the type of distribution is the conditional distribution of meat type for Chinese orders. What does meat look like, and how is it distributed amongst the Chinese orders? So the reason why we call it a conditional distribution, it's because we are looking at the distribution of one variable for a specified condition on the other variable. So we set a constant value for one of the variables. In this case, the constant value is Chinese orders. And then we're looking at how the other variable is dispersed within that one constant value, Chinese orders. So under the condition, we're choosing Chinese food. What does the distribution of meat type look like within that data set? So that's what we mean by conditional distribution. Under the condition that we are going to order Chinese. So we would probably ask questions like, what's the probability that she's going to want to order a beef plate? All right, so under the condition that she's going to order Chinese, what's the probability that she's going to want vegetarian? So that sort of thing. This is the reason why we call it a conditional distribution. So they want a relative frequency bar graph. Going back to what we saw in class, relative frequency differs from frequency in that it's scaled as a percentage or a proportion out of the whole, out of the sample size. So relative, or just frequency by itself, it's the number of observations. It's a count. It's a whole number. Relative frequency is the rate at which those observations occur for a particular category. So rate or percentage means we're going to divide by the total. So relative frequency just means percentage. So that's what we gave here in this Pareto diagram. I gave a percentage. That's a relative frequency. And this isn't the same word frequency as like in a physics class. So this doesn't refer to like oscillatory motion or anything like that. Frequency just means how frequent did this thing occur? How many times did it occur? So it's a little different in statistics. Sounds like a very, very fancy word, but it's not as fancy as it could be in physics. So letter B, relative frequency bar graph showing the conditional distribution of meat type for Chinese orders. And I'm going to start off with a bar graph with a y-axis and an x-axis. And I don't think I need that long of an x-axis because food type or meat type is limited to just 3 choices. So this is meat type, and there are 3 types. Beef, in this case. Obviously, they're leaving out one of my favorite types, in this case, pork. And Chinese definitely do utilize pork in their cooking quite a bit. There's chicken. They also use seafood a lot. But we're just going to simplify it, and we see these 3 options here. So this is fake data, obviously. But either way, beef, chicken, veggie. And we want relative frequency, so I'm going to go ahead and put that in the form of a percent. So you don't have to make that a percent. You could put proportion, or you could just write relative frequency and leave it as a proportion value. Proportions are between 0 and 1. So decimals, but back, percentages back in decimal format by dividing by 100. Between 0 and 1 instead of between 0 and 100%. So in this case, I'll just go with the percentage. If it's a relative frequency bar graph, you're safe to use percentages. So I got to find out what those percentages are within Chinese orders. So beef, 14 occurrences out of the 44 total Chinese orders. So here I have a calculator with no shame. I'm just going to divide those. 14 divided by 44. 0.318181818, and it keeps on going. So I'm going to round that to the nearest tenth of a percent. So 0.318, or 31.8%. So this one is, I'm just going to write it on the bottom, 31.8%. And then I'm going to go ahead and I'm going to use those numbers once I'm done with all 3 to figure out what the scale is going to look like on the y-axis. So chicken. There were 18 observed chicken values for Chinese orders. So 18 divided by the same 44, 40.9090909. So if I round that to the nearest tenth, 40.9%. The other one was 31.8. Looks a little weird. And then vegetarian, if I just add those 2, subtract from 100, I should be good. I'm just going to continue since I have the calculator anyway. 12 divided by 44, 0.27272727. So 27.3%. And I got to check to see if those add up to 100%. The 0.8, 0.9 make a 0.7 in the end, and the 0.3 in the end here will add with that 0.7 to make a 0.0. So I'm not even going to check if it's going to add up to 100%. I just care about the last digit. And as long as it's a 0.0, I'm pretty sure we're good. And then I'm going to go ahead and see if I can figure out a scale for that. I'm going to cut it just like I did that previous one where we didn't start at 0. We still have an even linear scale, so these tick marks have the same numerical value between them, 5, 5, 5, and so on. So I'm going to do the same thing here where I cut it and started it at 35. So I'm going to cut it here and start it where? Maybe 30? No. 27.3. So maybe I might want to start at 25. I don't have to write percent on that because I wrote percentage up on top. So those are units and what it is at the same time. And then the largest I see is 40.9, so I might want to make that 40. So 25, 30, 35, 40. So that's 40. This was 35, this one's 30. And it looks reasonable, so that's okay. So 31.8 should be somewhere around here, and I'm not going to draw grid marks like I did in that previous one. Did I draw grid marks in that one? Yeah, I did. So I went a little extra on that one. I'm not going to do that here. As long as it's reasonably drawn, no big deal. Chicken, 40.9. 40.9 is going to be a little bit above that 40. And just eyeball it. Make sure it's accurate somewhat. And then now that I'm going to hide my sources there, those numbers. I'm going to play it off as if I had already known those and done them in my head. So veggies 27.3. 27.3 would be somewhere around here. And there's our relative frequency bar graph. And this is showing the conditional distribution of meat type for just Chinese orders. So here, Because it's a conditional distribution, it is a very good idea to give a title for this. These are Chinese food orders. So that way we make no mistake. These are only for Chinese food orders, and this is the percentage distribution of the type of meat within just Chinese food orders. You can box that if you want. Make sure that you know that that's the title. And if you want to even make sure that the grader, whoever that is, if it's the real AP exam, you can say title and make it obvious. So that way there's no guessing that that's actually the title. But you don't need that. So that's it for letter B. So you're literally just drawing a bar graph, and conditional distribution is just a fancy vocabulary term. You need to know what it is though, and it just means that under the condition that we're only paying attention to Chinese food, what does the distribution of meat type look like? Right? So they could have asked for the conditional distribution of food style within the vegetarian situation. So let's say she's feeling vegetarian that day. It's Amy who's making these orders. Let's say she's feeling vegetarian that day, or she doesn't want meat that day for whatever reason. Then we can start asking questions on like what style of food does she prefer to have veggie with, right? So then that would be another conditional distribution. So under the condition she wants vegetarian food, then what does the other variable look like? What's the distribution of food style within that one condition? So we could have easily asked a question like that. So what we're doing is we are setting one of the variables constant, and then we are looking at how the other variables distributed amongst that constant variable value, which is exactly what we did with the Chinese orders. We set that food style constant, only in Chinese, and we looked at the distribution of meat type within that one constant value. This is actually a two-dimensional distribution. You can think of it as like a function of two variables as opposed to just one variable. And what we're doing is we're setting one of those variables constant. We're plugging in a value for one of the variables, not the other, if you want to think mathematically. Okay, what if I wanted to compare both variables at once and try to see if I can look at the distribution of one variable across all values of the other? First off, that's what the table's for. The table kind of gives us an idea of what those distributions look like. Problem is these totals in the bottom are not scaled by percentages. So these numbers here need to be fixed so that they show sizes relative to the total, because these totals differ. So you might want to come up with a scheme where all of those get changed to percentages with respect to their corresponding totals. All right, so what if I'm interested in seeing visually all conditional distributions at once for all types of food styles? So not just the Chinese one, but I want to see it for all styles. There's a way to do it in another bar graph. It's like a two-dimensional bar graph, but it's not going to look weird. It's going to still look like a one-dimensional bar graph, but there's a way to add a second dimension in there without adding a z-axis in there. So there's two ways to do it. We have a side-by-side bar graph, where in that situation, we'll go by percentages, and then we're going to show multiple bars instead of just the one bar, where those multiple bars will correspond to the different values of that other variable that we're varying, or a segmented bar graph. A segmented bar graph is another way to do that, but it's going to be done vertically instead of side by side. So instead of horizontally, it's done vertically. And we are going to segment those vertical bars, so that way those segments have sizes proportional to the actual distribution percentages of that one variable distributed in that other conditional value. That's quite a mouthful, but you can go ahead and read those definitions. It's very tough to give a precise definition for those things, so that's why they're kind of wordy. They're big paragraphs. It's easier just to draw them and to see what they look like. So instead of me going through the actual reading the definitions for you there, you can go ahead and try that on your own if you want, but it's easier for us to actually show what those look like, and you kind of get the idea of what they are once you see how they're used. So we're going to construct an appropriate, so they're going to give me the freedom to choose one or the other. Construct an appropriate graphical display that reveals the association between meat type and food style for this data. So if they give you the choice, the one I recommend is the segmented bar graph, always. Segmented bar graph is much cooler looking. Side-by-side bar graphs can look really ugly depending on how good you are at drawing. But they can look very disorganized. And if you don't really use, if you use frequency instead of relative frequency, it's going to look very meaningless. So I'm going to go with the segmented bar graph because it scales for percentages. So construct an appropriate display that reveals the association between meat type and food style for this data. Then comment on this association for this data. So I want to see how those two variables play with respect to each other. So the idea is, I'm going to go with the same idea here. How is meat distributed within just Chinese orders? Then let's ask the question, how is meat distributed across all types of food styles? So here's how we get this done. So I'm going to draw a bar graph. I'll start with a bar graph, y-axis and an x-axis. And how many food styles are there? There's 5. And because there are 5 food styles, I need to make this x-axis a little longer. So food styles. Zoom in a little. See if I can zoom in more. Yes. Okay. So then food orders or food types. It was Tex-Mex, Indian, fast food, Chinese, and it was Middle Eastern. So then what we're going to do is we are going to show some visual display using bars and a bar graph of what's going on in the table. So I already have it vertically. Tex-Mex is vertical. 19, 13, and 12 are the frequencies within just the Tex-Mex condition. So what we're going to do is we're going to draw a bar that translate those numbers into segments of proportional sizes to those numbers, 19, 13, and 12. So 19, 13, and 12 out of 44. What I'm going to do is a bit of math. I'm going to find out these conditional relative frequencies out of 44. So 19 divided by 44, 13 divided by 44, and then 12 divided by 44. So we'll get that done. So 19 out of 44 is 0.432 approximately. So I'll round to the nearest thousandth. And that's the same thing as rounding to the nearest tenth of a percent like I was doing earlier. So 13 divided by 44, 0.295. So what I'm going to do is I'll go ahead and edit out where I actually write all these percentages for the corresponding, or all those percentages for each of those cell values. It's going to be done vertically. So it's the cell value divided by its corresponding column total. So I'll get back to you once I have all that done. And there's the completed table. So there's all the values calculated. They're rounded to the nearest tenth of a percent or the nearest thousandth in proportions. So then what we're going to do is we're going to draw a bar where the segments are this large. And we'll see how that's done. That's going to be out of 100%. So we are going to have a bar for each of these 5 different values of food style. And we're going to set that at 100%. So again, I'm going with relative frequency here. So all of them are going to have the same height. The difference is how those segments are going to look inside out of the total 100%. That's where they're going to differ. Make sure they're approximately the same width. That way the only visible differences should be between the sizes of the segments themselves along the vertical axis. Okay, so then we segment these. So I'm going to have to figure out an even scale, make it a little accurate, 25%, 50%, 75%. And you know what? That's about as accurate as I'm going to get, or that's about as zoomed in we're going to get. And then we'll just eyeball it. So over here, for Tex-Mex, we have beef, chicken, and veggie. And I could do them in the same vertical positioning that we have them here. Veggie's the bottom segment then. Beef is the top segment. Chicken's the middle segment. So 27.3% for veggie. Veggie's going to take up a space that's just slightly bigger than 25%. Just eyeball it. And I'm going to leave the vegetarian one not shaded in. And then what I'll do is I'll gauge what the top one should look like and the middle one, if both of those other ones were done accurately, should also be accurate as well. So 0.432 for beef at the top, 0.432, so 43.2%. So there's 50%, 43.2%, somewhere below 50%. So vertically, it's going to be above, right? Because I'm scaling it from the top going this way in my mind. So then I'm not going to shade in the bottom. I'll shade in the middle, maybe this way. And then I'll shade in the top, maybe this way. And that's going to show the differences between the segments and how to pick them off visually from each other. So then here's the rest of that bar graph segmented. So what's missing here, I've already labeled both of my axes. When it comes to a segmented bar graph like this, when there's separations here where these different shading schemes could mean something or could have meaning behind it, you want to tell the reader what the meaning is in the form of a key or a legend. Call this a key. And what you'll do is you'll provide boxes with the same shading scheme and then give an interpretation or explain what that shading scheme means. So this is going to be at the top. It was, I don't remember exactly what it was. The top was beef. Is that what it was? Yeah, top was beef. The middle was chicken. That's the one that's shaded this way. And then the one that wasn't shaded at all was vegetarian. You could box that if you want. Underline key, not a big deal. And then it's going to ask us for something else. So I zoomed out too much. Then comment on this association for this particular data. So they wanted a graphical display that reveals the association between meat type and food style. How are those related to each other? How are these two variables distributed within each other? And then comment on it. So when they ask you to do that, and we have percentages, percentages can allow us to make meaningful comparisons between these variable values within these other conditional variable values. So since what we did was we showed the percentages of meat type within the food styles, then I'm going to compare the percentages of meat type for each food style. So then you start looking at the sizes, the relative sizes of these things. And if you look at the numbers that we wrote up there, because maybe my drawing isn't accurate enough, but one of the things you'll see, Tex-Mex and fast food, if I go back to the numbers that we wrote here, beef was the one that was most frequent, and vegetarian was the one that was the least frequent. So when ordering Tex-Mex or fast food, Amy tends to choose beef meat or like beef dishes, and is least likely to choose vegetarian dishes. So I'm going to write that in. And I'll let it bleed over outside of the page. So then when fast food is ordered, or Tex-Mex, so it's Tex-Mex or fast food, Amy is most likely, so there's context involved. I named the person because the person was named, and I'm giving the names of the variable values. Fast food, Tex-Mex, is ordered, so we're ordering food. So there's context involved. So we're not just stating the largest percentage here was for beef and the smallest percentage was for vegetarian, without explaining what the context is. So Amy is most likely to order a dish with beef and is least likely to order a dish without meat or vegetarian. So let me read that again because the handwriting's kind of bad. And the faster I write, the uglier it looks, the more chicken scratch-like it is. So when fast food or Tex-Mex is ordered, Amy is most likely to order a dish with beef and is least likely to order a dish without meat. I left out chicken because there's only 3. In a situation where there's 3 values, you want to state which one's the highest and which one's the lowest, and then you apply that other one is in the middle. So you only have to state which one's the highest which one's the lowest in a situation where there's only 3 values. So that covers Tex-Mex and fast food. That doesn't cover Indian, Chinese, and Middle Eastern. So we start looking at the trends and where they might be similar. So for Indian food, it kind of looks like vegetarian is the most common option. I gotta go check the numbers just to make sure. And I would be wrong. 35 versus 41%. So the way I drew it looks a little misleading. Or maybe just the way I'm seeing it right now. But let's see. So for Indian food, she's most likely to get chicken, least likely to get beef. So most likely to get chicken, least likely to get beef. Any other ones that look like that? Chinese, most likely to get chicken. Actually, no, least likely to get vegetarian. So that's different than Indian. Middle Eastern, most likely to order chicken, least likely to order vegetarian. So no, Indian is all on its own. She's most likely to order chicken, least likely to order beef for Indian. She's most likely to order chicken, least likely to order vegetarian for Chinese and Middle Eastern, which those also differed from Tex-Mex and fast food, in which she was most likely to order beef, least likely to order vegetarian. So I got to keep track of that. So for Chinese, Middle Eastern, most chicken, least vegetarian. What was it, Chinese and Middle Eastern food is ordered, I don't have to say Amy anymore because I've already named her. I could just say she. Though Amy and she have the same number of letters, so it's not like I'm benefiting by changing the word here. She is most likely to order, what was it, chicken? And least likely to order vegetarian. When an Indian order is made, Indian food order is made, she is most likely to order chicken and least likely to order beef. And there we've described the distribution of meat type for every single food style. And we've lumped together the ones that were like each other categorically. They shared the same most likely and the same least likely. Or they had the same ranking scheme, basically. So that's kind of a large response. But that's a response that you're expected to give for something like this. And that's something you're going to want to get used to. AP exam is going to have a lot of writing like this. Okay, so for number 4, they're going to want us to construct a side-by-side bar graph here. Let me go ahead and read this. Each year, the Princeton Review conducts surveys of high school students who are applying to college and of parents of college applicants. The report in 2009, College Hopes and Worries Survey Findings, that's the Princeton Review, included a summary of how 12,715 high school students responded to the question, ideally, how far from home would you like the college you attend to be? Students responded by choosing one of 4 distance categories. Also included was a summary of how 3,007 parents of students applying to college responded to the same question, a similar question. How far from home would you like the college your child attends to be? And then we're going to compare those 2 distributions. So in this case, we have data in 2 different populations, or data taken from 2 different populations, and we're going to compare how those populations are distributed with respect to this ideal distance variable. So the accompanying relative frequency table summarizes the student and parent responses. Construct a side-by-side bar graph to compare responses regarding ideal distances for each of the 2 samples. So then the same idea applies. We're going to have a side-by-side bar graph, and what we are going to do is we're going to probably scale them to percentages. Side-by-side bar graph, they gave us the freedom to either report frequencies or relative frequencies. You're always better off with relative frequencies. Unless they ask you specifically for frequencies, you're going to want to go with relative. So if they asked you specifically for frequencies, not relative, you're going to have to do what they're asking for. But in this case, since they didn't specify, I'm going to go with the better one, which is relative. Because relative scales for size differences, and you're going to notice that the total totals, which I'm going to go ahead and add up, they're going to start decreasing as distance increases. So 4450 plus 1594 is a total of 6044. So that's the column total for the first, less than 250 miles away. So those are the people who are answering the ideal distance is less than 250 miles away. The people out over here, more than 1,000 miles away, where the parents and the students really hate each other. They want to be really, really far away from each other. So either way. Or maybe they have a specific school in mind and it's just, how far away that is from where they actually live. Maybe not necessarily that they just want to be far away. It's just the school that they have in mind is really that far away. It's 3942 plus 902. 4844. 2416 plus 331 is 2747. So you're seeing that we should be seeing that the most frequent category is this less than 250. I don't want to be too far away. So 1907 plus 180, 2087. And then we'll look at the total. So what is the combined sample size? Which I don't think I need that one, by the way. Since that's not an actual category, it's not going to show up in the bar graph. And I don't need it for the calculation of the percentages. So what I'm going to do is I'm going to translate these now to percentages. 4450 divided by 1594. And I don't know if I want to go with those percentages. So a side-by-side bar graph. We want to see if we can scale this appropriately. And if I do this by percentages out of the column total, we're going to be robbed of some information. And what information am I going to be robbed of? So in the segmented bar graph, we didn't want to see how these categories differed: 44, 48, 37, 44, 52, and so on. So that didn't actually matter. We just wanted to see the percentages of meat type within each food style. So then we scaled it so that way they were all going to add up to 100%, so I can actually see which segments were bigger than others. That's not the case here. Yes, I want to see which bar set up by the sides to each other are bigger than each other, but we don't necessarily have to do that with a percentage out of just the category. I might want to change those to percentage out of the sample, since these are different populations. So it's just a personal preference. It's maybe some sort of maybe a professional choice ahead of time that I'm making, or some sort of it's just something so that way we can see this decreasing pattern. So I'm seeing that this pattern is decreasing. That is an interesting pattern that I want to come out in the final graph. So I don't want to have those adding up to 100% total with the bars being the same height. I want to scale by the sample size instead. So what I'm going to do is I'm going to divide the 4450 by the sample size 12715, and that's going to be the percentage there. So I'm going to make some comparisons based off of that. So 4450, and the reason being it's because those samples are different. These are two different types of people. It's not like they're all food orders. These are different types of people, students versus parents. So you want to scale it for the type of person that we are studying, whether it's parents versus students. And I want to see how these percentages across this way will differ, and so on. So 4450 divided into 12715. And it's going to be hard to write that in there. So I might want to zoom in quite a bit. If it lets me. It doesn't look like it's going to. There we go. 34.99, so that's about 35%. So I'm going to write those in percentages. 35.0, that looks like an 8. 3942 divided into 12715. So that's 31.0%. 2416 divided by 12715. So finally, once those are done, We construct a side-by-side bar graph to compare responses regarding ideal distances for each of the two samples. And here's why I figured I wanted to do this across the samples. So we wanted to show how ideal distances compared across each type of sample, each type of person. So I divided by the total for each type of person instead of vertically. Okay, so we want to construct a side-by-side, and side-by-side means this. You'll draw another bar graph, y-axis, x-axis, and we have 4 distance categories. Less than 250 for the first one, so less than 250, 250 to 500, 500 to, I think that's supposed to be 1,000. That's a typo. So 500 to 1,000. And the last category, greater than 1,000. And this is distance, which you don't want to leave out the quantity. The name of the quantity is distance. And then you also want to give, if you can, units. That'll be in miles. What you want to make sure you don't do is just give units. Units are meaningless. Right? So sometimes unit names are shared amongst other physical quantities. And not just physical quantities that we're measuring any type of phenomena. So units sometimes don't really give much context. You want to name the variable. In this case, it's distance that we're measuring. It so happens that we're measuring in miles, but the miles is not the important part. It's what we're measuring, distance. And then what we're going to do is for each of these 4 categories, we're going to draw 2 bars right next to each other, hence the name side-by-side bar graph. And what I'm going to do is I'm going to look at these percentages and figure out what my scale should be. Lowest number I see is 6. Largest number I see is 53. So I might want to go just from 0 to 50, and then the 53% will just go a little higher. So I'm not going to cut it. I'll have it at 0. Let's say 10, 20, 30, 40, and I'm just eyeballing it, making sure that they're semi-accurate, at least semi-accurate. And then we have 50%. And these are percentages. So for the 250 category, less than, we have 53% for parents, 35% for students. So 53%, that's going to go all the way up over here. 53%. And then 35% for students. And because these are going to be different bars, you're going to want to have some mechanism for showing how these differ and separating them. And I'm probably going to come up with a key. I'm going to do unshaded for the one on the left, shaded for the one on the right, and the one on the left is students, the one on the right is, oh no, I did parents first. Okay, so I'm going to have to keep that in mind. So key on the left, unshaded, parents. On the right, shaded, students. So I got to make sure that I'm not messing that up again. So now I got to stick with that, keep it consistent. So parents is 30%, students is 31%, so they're pretty close to each other. So just a little bit higher than 30%, and just a little bit lower than that one at 30%. So I'm going to leave it so that way there's a visual difference, an apparent difference between the two in height. It doesn't have to be super accurate. And then for the next ones, 11 on the left, 19 on the right. So 11 on the left, a little higher than 10. 19 on the right, a little lower than 20. And I'm just eyeballing it, should be somewhere there. Something like that. Greater than 1,000. 6 on the left, 15 on the right. So 6 less than 10. 15, which is between 10 and 20, which I didn't draw any grid lines, and I'm just eyeballing that to the best of my ability. And there we are. So the reason why I did this by calculating percentages out of students, now I can go ahead and say which one's larger, which group was more likely to state this distance. So it looks like students were most likely, I'm going to have to reword that. we had a higher percentage of students than parents that chose the larger distances, 5,000 to 1,000, greater than 1,000. So there were higher frequencies for students in those categories compared to parents. Parents had a lower frequency. So how would I word that specifically to make that statistically accurate? So there is a larger percentage of students, and that's compared to parents, that prefer or have an ideal distance for the campus. So here I'm butchering the context. I'm just making sure that I write everything I need to. It doesn't necessarily have to flow beautifully English-wise. So have an ideal distance for their campus of choice, or we could just say their campus. So their ideal campus distance away from home, that probably be a better wording for that. In the larger distance categories. And the two larger distance categories are 500 to 100,000, or 1,000 miles, and the other distance category greater than 1,000 miles. So then we also had the percentages were larger for parents that had a lower ideal distance category. So the same would be true, but the opposite in those other two categories, which I'm not going to go ahead and write it for the sake of time. Let's see. I think I was answering letter B. So one thing here you want to make note is you read everything, all parts there before you start answering things. So letter B, describe differences and similarities in the ideal distance responses for the two samples. So I started already the answer for letter B. So that's where I'm going to go ahead and stop, but that should be down here. And that's only the first half of the response. That's not the entire response. And from what I understand, that's it for this particular handout. So that's everything that we missed in class today because I didn't time this stuff right. So this will be on the Google Classroom. Make sure you guys go over it and use this for the practice problems I'm going to give you guys over this particular section. And that's going to be it for today.